So we're starting 5.4 today. We're looking at rational functions, which we've been looking at for the last couple of sections, but today we're talking about the graphs of those rational functions and some aspects of those graphs. You actually will not need a graphing calculator for what we're going to do. We're really going to look at the equation and say, what can I tell about the graph just by looking at the equation? So we're going to do this a little differently. I'm going to look at these 4 problems. Okay, now you'll notice that your instructions for all 10 problems are the same. They ask you to find the holes, the vertical asymptotes, the x-intercepts, the horizontal asymptotes, and the domain for each one. So instead of breaking it up into different sections, I just put them all for each problem. You'll see that that's actually helpful because a lot of the work you do for one is exactly the same steps you do for the others. So especially finding holes, you're going to do everything you do to find the holes will actually set you up to find everything else. So that's why it's set up that way, but that'll make more sense in just a second. So we're going to look at these 4 problems, 3, 4, 5, and 6, because they each have all the different parts to them that we're going to need. For each one of these, I'm going to start by factoring as much as I can. So let's see here. For this one, if I factor, I'll factor an x out. That gives me x squared minus 16. Factor a negative 4 out. That gives me x squared minus 2x minus 3. Now, hopefully we remember that this right here is a difference of squares, which means I can factor that into x times x plus the square root of 16 is 4, x minus 4, okay, all over negative 4. Well, let's see here, what can I factor this one into? I know it's x, I know it's x. Well, negative 3 is negative 3 and positive 1, or positive 3 and negative 1, but those two numbers have to add to make negative 2, so that's why I put the negative with the 3. Alright, so I factored it completely. Great. I'm going to go ahead and do the same thing for the other 4 before I get back and actually talk about, well, what do I do to find holes. So let's move on. I'll factor a negative 4 out of this one. If I factor out negative 4, that gives me x plus 3. I can factor an x out, giving me x squared plus x minus 6. Switch, and so can't do anything else to the top. The bottom I can change this. Let's see here. 2 times 3 is 6. And one's positive, one's negative. On with the 2 negative, the 3 positive, so they add to make positive 1. Come over here. I can factor this into, let's see here, 2 times 4 makes 8. Oops, 2 times 4. And 2 times 4, and 2 and 4 also add to make 6. Here I can factor an x out, giving me x plus 2, and that's all I can do with that one. Over here, factor out the a negative 3x. That gives me x plus 2. For this one, x plus 2 plus 1, because 2 times 1 is 2, 2 plus 1 is 3. There we go. We have them all completely factored out. Now we can get to each of our parts. So what I'm going to do is I'm going to go through and say, well, the holes. How do I find the holes for each one of these? Okay. Well, to find a hole, I'm looking for what cancels out. Okay. Well, let's look at number 3. If I look at number 3, I see nothing cancels out. Well, if nothing cancels out, that means there are no holes in this graph. Okay, simple enough. Well, let's move on. Well, what about this one, number 4? Well, number 4, I have an x plus 3 in the top and an x plus 3 in the bottom. I can cancel out that x plus 3. Get that out of my way. And so because I canceled out an x plus 3, that means I have a hole when x plus 3, which is what I just canceled out, equals 0. Well, how do I solve that? Well, I'll subtract 3 from both sides and get x equals negative 3. So I have a hole at negative 3. And then what that means is if I plug negative 3 in for x, the top of my fraction would be 0 and the bottom of my fraction would be 0. I get 0 over 0. I cannot have 0 over 0. I can't have 0 in the denominator, period. But when I specifically have 0 over 0, that's what tells me I have a hole in my graph. Let's look at number 5. Do I have anything top and bottom that cancels out for number 5? I have an x plus 2 and an x plus 2. I can cancel both of those out, and that leaves me with, well, let's set that equal to 0. I just canceled out x, oops, let's try a different color, x plus 2. So whatever I cancel out, I set equal to 0, solve for it, and I get x equals negative 2. That's the hole. Over here, number 6, I can see I cancel out x plus 2. So I canceled out x plus 2, so I set it equal to 0, solve for x, and I get x equals negative 2. Now, let's say you cancel out two different things. I don't know if that's going to come into case here, but it didn't come into any of mine, but it's possible. If I cancel out two different things, then I just have two different holes, and that's okay. So that's how I go about finding holes in my graph. Alright, I'm going to erase what I just did, but I'm going to leave the factored part because I'm going to need that to find the rest. So again, these build on each other, and that's why they're all doing them together. So the work we just did is going to help us on the next part. Okay, so I'm going to try to put that right there so it's out of the way. So I've already canceled stuff out that I could cancel out. For number 3, there was nothing. For everything else, I canceled out what I could cancel out. So next thing we're going to find is vertical asymptotes. For vertical asymptotes, which takes me a while to write, so I usually shortcut it and write just VA. Alright, so for vertical asymptotes, it's where the bottom equals 0, but not what I canceled out. Pretty sure it canceled out. It's supposed to have two L's, but that's alright. So I'm going to take what's in the bottom, the denominator, and set each part equal to 0, but I'm not going to include whatever I canceled out. Alright. So let's get rid of that, and let's find our vertical asymptotes. So let's see, over here. Now, I do need to set equal things that actually have x in it. So for instance, I have a negative 4 here. I can't set negative 4 equal to 0 because it's a constant. It can never equal 0. However, I can set x minus 3 equals 0, and I can set x plus 1 equals 0. If I do that, I end up with x equals 3 and x equals negative 1. So those are my vertical asymptotes. Alright, if I come over to problem number 4, I already canceled out x plus 3, so I'm not going to use it. Just what's in the denominator that I have not canceled out. I have an x, so set it equal to 0. I have an x minus 2, set it equal to 0. Well, I have x equals 0, and nothing I can do there, so x equals 0. Here I'll add 2 to both sides and give me x equals 2. Those are my vertical asymptotes. I had 2 of them in both 3 and 4. Let's look at 5. I already canceled out my x plus 2, so I just have an x left. So I'll say x equals 0, and that's it. There's my vertical asymptote. And then come over to number 6. For number 6, I have an x plus 1. I have an x plus 2 as well, but that x plus 2 is canceled out. So x plus 1 equals 0. So if I subtract a 1, I get negative 1. There is my vertical asymptotes. All right. So vertical asymptotes are when the denominator equals 0. And I have a vertical asymptote because, well, I cannot let the denominator equal 0. So whenever x is, whatever x values give me a vertical asymptote, they make me have a vertical asymptote. Or sorry, whenever the denominator is 0 and the top is not, that gives me a vertical asymptote. It's an imaginary line that my graph cannot reach, so it goes to infinity. Now, the next one they asked me for is x-intercepts. Well, x-intercepts are when my graph touches the x-axis. Well, my graph touches the x-axis when it equals 0. A fraction equals 0 when the top is 0. So x-intercepts, which I'm just going to shorten to that, is when we set the top equals 0, but not what we canceled out. Okay, so basically the same thing we did with vertical asymptotes, except we're doing it to the top, not the bottom. So let's look at this one. What's left on top? Well, I have 3 things on the top. So I'm going to say I have x equals 0, x plus 4 equals 0, and x minus 4 equals 0. 3 different things on the top. Well, there's one. If I look at that, that's going to give me x equals negative 4. And this one's going to give me x equals positive 4. So I have 3 different x-intercepts. Over here, there for number 4, there is nothing on the top that has an x in it that I haven't canceled out. I canceled out the x plus 3, so I can't use it. There's a negative 4, but I can't set negative 4 equal to 0. So for this one, there are no x-intercepts. Okay. Look at number 5. Number 5, I canceled out the x plus 2, but I still have an x plus 4 left on top. Set it equal to 0, and I get an x-intercept of x equals negative 4. Come over to number 6. Well, what's on top that I haven't canceled out? I see a negative 3x. Or if you're thinking of this as just 2 different terms, I could think of this as just an x, but either way, set it equal to 0, divide by negative 3, and I get x equals 0. I have an x-intercept at 0. That's how I find x-intercepts. Alright, so let's get rid of those. Alright, so now we're at horizontal asymptotes. Horizontal asymptotes are the one thing that I can find without factoring, or without actually doing anything. Alright, to find horizontal asymptotes, I can look at the original. So for horizontal asymptotes, which I'm going to call HA, there are 3 cases. The first case is we're looking at, I should back up and say we are looking at the degrees, which if you'll remember is the highest exponent. Well, my first case is when the highest exponent of the top is greater than the bottom. Okay, well, if the highest exponent of the top is greater than the highest exponent of the bottom, then I have no horizontal asymptote. Well, let's look. I have 4 different problems here. are there any of these problems where the highest exponent of the top is greater than the highest exponent of the bottom? I'm looking down here at number 6, nope. 5, nope. 4, nope. 3, yes. 3 is greater than 2. So this one has no horizontal asymptote because the exponent of 3 in the top is greater than the exponent of 2 in the bottom. Okay, so that's case number 1. Case number 2. Well, what if the highest exponent of the top is less than the highest exponent of the bottom? Okay, well, again, numbers 5 and 6 are the same, so that's not the case. But number 4, I have an exponent of 3 here, but only an exponent of 1 in the top. Well, whenever the exponent of the top is greater than the bottom, my horizontal asymptote is y equals 0. Always y equals 0. Every time the top exponent is less than the bottom exponent, your horizontal asymptote is y equals 0. Doesn't matter what all the other numbers are, y equals 0. Okay, so that's what that one is. All right. Now we already answered number 4, so I'm going to write in a different spot now. We'll come down here. Well, what's case number 3, our third and last case for horizontal asymptotes? Well, what if the top equals the bottom? Well, I see that here and here. I also see it again here and here. Well, for both of these, we have a horizontal asymptote. Horizontal asymptotes are always y equals. Okay. And it's the leading coefficient divided by the leading coefficient. What I mean by that is the leading coefficient divided by the leading coefficient. So here, -3 is the leading coefficient of the top, divided by 1, the leading coefficient of the bottom, which of course is just y equals -3. If I come over here, well, the leading coefficient of the top is just 1. The leading coefficient of the bottom is just 1. So it's 1 over 1. So it's y equals 1. And those are my horizontal asymptotes. All right. So we're almost done. The only thing left to talk about is domain. And we actually did all the work for this one already. So let's get rid of my horizontal asymptote stuff and talk about domain. All right. Domain is all real numbers except wholes and vertical asymptotes. Okay, so for number 3, my domain, which I'm going to lose to capital D, is all real numbers numbers except, well, what did we get as our holes in domain? We didn't have any holes, but we had our vertical asymptotes at x equals 3 and -1. So that's my domain. I'm going to just go straight down to number 3, 4, 5. Maybe you're looking at like all real numbers except. That's 4 words, and I've already taught you that mathematicians don't like to write words, and you're right, we have a notation for this as well. So all real numbers is a double R. You can use that for all real numbers. So this right here means all real numbers. And except means not equal to. Okay, and so all real numbers except, what numbers can I not put? Well, we had a whole at -2 and a vertical asymptote at 0. So that's my little shortcut notation that I'm gonna write. They write their answers out as like in words, probably to not confuse you, but if you want to use a shortcut notation, you can. Let's look at number 6. I'm going to say that my domain is all real numbers except, so not equal to, well, I had a whole at -2 and I had a vertical asymptote at -1. So there's my domain. And then let's go back and do number 4. Alright, so my domain is all real numbers except, well, I had a whole at -3 and then I had vertical asymptotes at 0 and 2. And if you're wondering, no, there is no real order to what I'm putting them in. Some people always put their numbers least to greatest. I just listed them out anyway. I happen to be seeing them, so it doesn't really matter which order you put your numbers in. And that's it. That's all 5 elements we needed to cover. So good luck with that, and I'll see you on the next section.